We addressed one thing attached to our central atom, which is going to have to be a line every single time, and then the 3 dimensions don't really matter because it's all in a plane. When you have only 2 things attached to your central atom, it ends up in the same plane again, and so you can draw your Lewis structure planning ahead to account for the 3-dimensional geometry, like this. If you have 3 things attached to a central atom, you can spread things out visually. That'll all fit in a plane, and so you don't need to do anything special. And then if you put them 120 degrees apart, your Lewis structure will match your molecular geometry. Similarly, if you have a non-bonding pair replacing one of the attached atoms, like the atom is not there, but the non-bonding pair is, you can draw it in one plane, and you can continue to do that. Once we got to 4 attached atoms, then we had to swing from what we might expect on paper, which is 90 degrees, to reality, which is 109.5 degrees as we spread things out. And we just saw that this is coming out of the page and going into the page. So what happens then when we have 5 things attached to our central atom? And the answer is, you end up with something like this. And we can see from here to here there is a straight line. And then if you look at this from above, where you can see this, and this 120 degrees apart, now we're taking this and this and this and the central atom in one plane. And then we have one atom that is coming out of the page, that's this one here, and we have one atom that's going into the plane of the page, and that's that one right there. And so that is trigonal bipyramidal. I don't think it's worth memorizing any special bond angles here, because you already know the bond angles. I think most of you can spot that, like, from here to here we have a right angle. And I think most of you may recall from here to here, that's 120 degrees, right? It is as if we have a trigonal planar and a linear together in one structure. In fact, so we can think of this as a trigonal planar with a linear, all right? So what happens when we start removing things? Well, the first thing to note is, do I remove something from above or below, one of our pink ones here, or do I remove something that is on the plane? And for trigonal planar structures, it turns out that energy is minimized when you remove something that is in that trigonal planar arrangement, so one of those things. And then I will toss in, for our purposes here, our non-bonding pair, all right? So we see this is still there. We have this and we have this out of the board into the board or the plane. And the way that you can then look at this, maybe it'll be a little easier if I exaggerate these features, is this type of shape here. It's as if we have a fulcrum and then this is tipping back and forth, which gives us some idea, I guess, of the name of this, which is seesaw. And let's try and draw that over here. And so I've still got one thing going into the plane of the page, and I've got one thing coming out of the plane of the page, and then I have my non-bonding pair right there. Once again, there it is, and it is called seesaw, and you can see that if you look at it this way. Tip, 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 tip. Yeah. The only bond angle note of interest that I would put here, and again, I don't recommend memorizing this type of bond angle, but right here, this is going to repel slightly more than a bond would have. So you might end up with less than 120 right there. I don't really want to write it, but we can. Less than 120 degrees. And that is for the same reason that trigonal planar based bent was less than 120. That single non-bonding pair squishes it down a bit. We can keep removing from this, and we will still be removing things from that trigonal planar center. So I'll pull that off. And then we have 2 non-bonding pairs. And just so it's easier to see without them, I can set it on the page like this. And you may notice that distinctly, if I turn the camera sideways, it looks like the letter T, which happens to be its name. It is T-shaped. And I'll draw that in. Central atom, one above, one below, one on the side, with some non-bonding pairs. And there's other ways that we could draw it that make it match more that scheme, but I think it's cleaner if we just kind of keep going the way we did. And again, non-bonding pair non-bonding pair, which may be above and below the plane, but that doesn't affect us in how we're drawing that. You can remove this last attached atom and then have 3 non-bonding pairs around that central atom. And then you would end up with a linear geometry, and we can draw that in. Again, it's not really a situation you're going to run into too often. Maybe RNF2 would be an example of that, but again, we've still got our 180 for those, and then non-bonding pairs like that, and it does end up linear. I did not write there that that is T-shaped. And then bond angles, I think, are pretty self-explanatory for that. Now we bump up the difficulty 1 notch. Instead of 4 attached atoms, what happens when we have 5? In that particular case, we're going to end up pushing this over a bit, and we're going to end up with 4 atoms in the plane, and then still 1 above and 1 below. And it's going to look something like this. And you'll notice that it is 90 degrees in every direction, and we have a total of 6 things attached. And that's what we call an octahedral based structure. Central atom, 1 above, 1 below, into the plane, out of the plane, out of the plane, into the plane. And every single angle we have there is 90 degrees, so again, I wouldn't do any memorizing of angles, bond angles, because they're all 90 degrees. Let's write that name down, octahedral. And I want to, in a moment, get into some other naming for things, which at least might make the pictures more meaningful to you. When we remove something from our octahedral structure, it turns out, unlike trigonal bipyramidal, where we remove things from the plane, that trigonal planar center part, instead of above and below, for our octahedral geometry, it minimizes energy by removing the atoms that are above or below the plane. So if we do that, and I'll temporarily put in our non-bonding pair there, we end up with that non-bonding pair above or below the plane. We end up with that right there. And so we need a way to draw it. And all I'm going to do is not draw the bottom and put a non-bonding pair on the bottom where it was. So we have our central atom. Now we have a non-bonding pair down there. I have an atom going into the plane, coming out, oops, coming out, going in. And they're all still 90 degrees. Wow, that one ended up ugly, I'm sorry. So this, just like we had for our tetrahedral, trigonal pyramidal, that's a 3-vertex base. Now we have a 4-vertex base, which is square pyramidal. Just like with trigonal planar, where we took from the plane and from the plane, for our octahedral, if we remove, we're going to remove the other atom from the plane, which will leave you with something like this. And again, the reason it is that instead of tetrahedral is because that's not empty space. That location and that location have non-bonding pairs of electrons that are forcing these other atoms into a planar geometry. So to keep that in mind, this wouldn't end up tetrahedral because the non-bonding pairs are taking up that space. And again, I don't think this is a situation where sometimes you'll see people draw it pretty crazy. I think that's an easy way to draw it. 5 things in one plane. In fact, it is a square plane, and we can address it as such. Central atom, above, below, over, square, planar. And again, all 90-degree angles. From there, if we continue removing things following our VSEPR theory, and again, I keep putting these non-bonding pairs back in for comprehensive visualization, I'm going to pull this one out here. So now I finally get to take out from that plane right there. We have a non-bonding pair there. And this may look kind of familiar to you if you look at just those dark pink pipe cleaners. It looks rather like the letter T. And it is the truth that we now have another T-shaped that would be octahedral based. And 1, 2, 3, 4, 5, 6. However you wanted to put them on there. I did neglect to put my non-bonding pairs here, so non-bonding pair, non-bonding pair. Wow. Huge omission on my part, sorry. So we've got 3 non-bonding pairs on that central atom. It is T-shaped once again. If we pull off one more of our attached atoms and replace it with a non-bonding pair, you'll notice that we have a straight line. And as you look at it, it's kind of interesting to note, when we had just 2 things attached, it was linear. When we had 2 things attached with one non-bonding pair, that was trigonal planar based bent. It was like 120 degrees. When we had 2 things attached with 2 non-bonding pairs from tetrahedral, those 2 non-bonding pairs squeeze things a little bit more, and then our bonding will drop to under 109.5. Now when we add in that 3rd non-bonding pair, we end up with a situation where our structure ends up linear, and this is actually for linear for the trigonal bipyramidal at that point. So we start to show the exact same geometry, the electron geometries, and we see back to linear. In fact, when we add one more non-bonding pair, which is the case one step over from this, it follows our octahedral molecular geometry, but since 4 of those are non-bonding pairs, it just looks linear. And that's probably not a situation you're going to run into too often, but just for reference, we end up with linear again. Normally that's where you would end your learning of the structures or whatever, but there's one last one that I want to take a look at. And before we do that, I want to skip back a little bit to some of the names we had for our previous geometries.